Are you actually in control of what, when, and how much you eat? Maybe, but maybe not as much as you think. We love to say that weight loss is simple, just eat less. And technically, yes, fat loss does obey the laws of thermodynamics, but behavior doesn't, because what, when, and how much we eat isn't just about logic. It's orchestrated by our brain and it's regulated by hormones. Hunger isn't a character flaw, cravings are not random, and willpower is not the main driver of eating behavior. In this video, I'm going to break down the parts of our brain that dictate what, when, and how much we eat, and the key hormones that quietly run the show behind the scenes. We'll talk about meal initiation, meal termination, genetics, environment, diet structure, and where exercise fits into all of this. By the end of it, you won't just understand why you eat, you'll understand how to work with your biology instead of constantly fighting it. But first, who the hell am I to be telling you about this? I'm Linda. I have a bachelor's in molecular biology and a master's in biochemistry and biomedical sciences, which just basically means I'm professionally trained to obsess over how cells behave. And if that doesn't convince you, I also somewhat unhealthily consume, pun intended, everything I can find on health and fitness research, and then regurgitate it to anyone that will listen, which is right now you. Okay, so let's talk about the brain, the hormones, and why your appetite might not be the villain that you think it is. The hypothalamus is the brain's control center for hunger and fullness. It contains two populations of neurons. One population activates or promotes hunger, the other one suppresses it. Kind of like having a gas pedal and a brake pedal. Both are always present. And it's hormones, when they bind to these populations of neurons in the hypothalamus, that shift the balance between the two. When hunger promoting hormones are activated, they translate hormonal signals into electrical signals, which communicates with the brain's dopamine system. The hypothalamus signals to the VTA, the ventral tegmental area, the start of the dopamine pathway. VTA neurons release dopamine into the new name coming in, nucleus accumbens, also often abbreviated NAC or NAC. And NAC, let's go with that. Dopamine doesn't necessarily signal pleasure, it signals motivation and incentive. Like, this is worth pursuing, that feeling. The NAC is a gatekeeper to kind of like your motor center. It controls whether the brake on downstream motor systems is released. When the NAC is activated, it removes inhibition, which allows brainstem locomotor programs and motor cortex activity. This is what allows movement toward food to begin. Two other brain regions get a vote on whether you move towards food. We've got the prefrontal cortex. This is what most people, scientists, talk about when we talk about our intelligent brain, the brain that we kind of developed as humans that differentiate us from other animals. Here is where we do planning and create rules for ourselves. So the prefrontal cortex represents goals, long-term plans, social rules. For example, I'm on a diet or I already ate. This input can suppress food seeking even when hunger exists. The second part of the brain that gets a vote is known as the anterior cingulate cortex, the ACC. This is where effort and cost comes in. It evaluates the physical effort it takes to go do the thing you're considering, in this case, finding food, the time delay between you and the thing, and the opportunity cost. For example, if food is nearby, the effort is low. If food is miles away, the effort is really high. High effort can veto food seeking, even if you're in a hungry state. And then integration of these signals, these inputs happens at the nucleus accumbens, the NAC. It integrates the dopamine from the VTA, so the reward value, the input from the prefrontal cortex, so your plans and your rules that you've created for yourself, and input from the ACC, anterior cingulate cortex, effort and cost. And it's a weighted integration. Depending on which signal dominates, it'll either release the brakes, thereby allowing movement to begin, or the brakes stay on and you have no action. All of this happens even before food is eaten or even available. These are anticipatory behaviors. They include restlessness, food thoughts, increased attention to food cues, physiological priming to start moving. This produces the subjective feeling that we get, that feeling of hunger. And it exists to shift us from being at rest into action. So it prepares you to go obtain food. So the brakes are off the motor cortex, foraging begins. Searching, walking, opening cupboards, ordering food, cooking, and then meal initiation. That threshold is crossed where hunger and motivation outweigh your competing signals. You stand up and you begin to eat. You don't just feel hungry, you're driven to act. In fact, if the connection between the hypothalamus, that area of your brain again, tells you you're hungry or you're full, and the dopamine system, the next part of the cascade, is disrupted. So if we break that connection between the hypothalamus and the dopamine system, an animal can still be hungry, but it will not move towards food, even if the food is placed one body length away from it. So there have been mouse models to show if you cut that area of that animal's brain, it won't move towards the food even when it's hungry, and it will actually starve to death. What this shows is hunger without dopamine results in no action at all. But putting this all together, the hypothalamus is saying energy is low, or I usually eat soon. The start of the dopamine system, the VTA, is saying food is worth pursuing. The ACC is saying, here's the effort required. Your prefrontal cortex is saying, here are my plans and my rules. And then your nucleus accumbens, your NAC, integrates all the inputs and decides whether to release the motor brake, let you start moving towards food. So now let's look at some real world examples where you might be hungry but not eat. You might not be hungry, but you still eat, and everything in between. So the scenario in which you're hungry but you don't eat might be because you're dieting. So in this case, your prefrontal cortex vetoes the decision to go get food. Or food is too far away. In that case, you're hungry, but you don't eat. Your ACC is the one that vetoes, says it's too much effort. The last scenario here is depression or low dopamine. So you might feel hungry. You might not be on a diet. Food might be very close by. But because you're not producing enough dopamine for whatever reason, you don't have the motivation to go get the food. What about not hungry but still eat? Strong food cues. So dopamine release without hypothalamic input. For instance, if you see something super ultra tasty, you just can't resist it, even though you are stuffed. Or let's say you just ate a whole meal, but someone puts a bowl of chips in front of you. It's right in front of you, so it's very easy to get to. There's very little effort. This is your ACC saying yes. Sleep deprivation or stress weakens your prefrontal cortex. So even though you might have rules for yourself, or you just ate and your prefrontal cortex is saying you don't need to eat again, you might still eat in that scenario. Okay. All of that had to do with meal initiation, starting to eat. What about what determines when you stop eating a meal? Let's talk about the next part of the brain.